Okay, so picking up where we left off last time, we were talking about accumulating quantities, and we noted in particular old news stuff like mass is an accumulating quantity, and specifically, let me go back to that just real quick, accumulates over area in the sense that if you look at a whole area, and if you divide that up into two smaller pieces of area, right, then the quantity in question as associated to each of these smaller pieces, those two quantities add up to the quantity in question for the whole. So again, mass is an obvious thing. If you take mass and you cut it in half, it's the same total amount of mass, right? So of course it's an accumulating quantity. So here's the where we ended. We were talking about another, I'm going to say, surprising example of an accumulating quantity, and that is, mysteriously, given a certain vector field, I wanted to be in highlighter mode, boundary circulation. Mysteriously, seemingly, how could this possibly be, right, is an accumulating quantity. So, we walked through the details last time. I'm not going to repeat all that, but the big idea is when you look at the left half plus the right half, there's a temptation to say, well, wait a minute, these two pieces of a line integral there on this shared edge where you cut the whole into two separate pieces. On this red curve, you've got green line integral going that way. You've got blue line integral going that way. This is what's part of the circulation on the whole, the circulation on the pieces that simply isn't there in the circulation around the whole. So this would seem to be the problem right here, is these two terms. And the beautiful beautiful observation is that this is the same curve with two opposite orientations, and so they cancel. And so in fact there is no difference between boundary circulation around the whole versus boundary circulation around each of the pieces added. Okay, so that's what we were doing last time. Okay, now I'm going to point out that it also doesn't matter how you slice it. The argument that I make above is conveniently just the two pieces, right? The big idea, though, is that every time you make a cut through the middle, in other words, every time you introduce what you might call a new part of boundary, right? By cutting through the middle of things, there's always going to be part on one side and then part of the area on the other side. And so it doesn't matter how many times you cut it, this same sort of cancellation sort of thing is going to happen. So for example, supposing that I've got all of this area and of course more, and I'm just focusing in on the sort of part near the bottom, but a large region of area, and I cut it up into a bazillion little pieces, right? Well, when I do that slicing, I will, among other things, slice along that edge right there. And that is going to be part of a boundary circulation. In fact, it's going to be a part of two boundary circulations. It's going to be oriented that way as part of the region on the left. It's going to be oriented that way as part of the boundary of the piece on the right. Opposite orientations on the same curve, they cancel. Right, and then likewise on all the rest of these pieces. Let's see, so on this edge, well, it's going to be oriented that direction as part of the boundary of what's above it. It's going to be oriented that way as part of the boundary of what's below it. Opposite orientations, and they cancel. Right? This is just straight up going to happen on every one of these sort of new edges, you might call it. Every one of these where you cut. Right? All of these, they're all just going to cancel. Now, some edges will not cancel. For example, this edge right here, this little piece, this is part of the boundary of this piece above, oriented as indicated, but it doesn't cancel with anything because there is nothing on the other side to cancel with. So what do we do about the fact that this doesn't cancel? Well, good news, it's not supposed to cancel. After all, it is part of the boundary of the whole that we want this to all add up to in the first place. So everything just kind of works out perfectly. And again, mysteriously, counterintuitively, these boundary circulations always cancel. Okay. All right. Now I'm going to give you a weird point of view on this. It's going to seem weird. I claim it's ultimately very natural. But this does take a little bit of digesting. This is a big bite to have to chew on. So the idea is this. Even though boundary circulation is computed on the interior, even though it's computed on the boundary, after all, it's boundary circulation, you can, and I claim should, think of it as something that's actually happening on the interior. It's very weird to think of it this way. How could something that's computed over there actually happen in the middle? And the way to see this is, according to what makes sense to me, everybody's different, of course, is to recall that what we're talking about is quantities that are accumulating over areas, right? So when I say that some quantity, whatever it is, accumulates over areas, what I mean is if you have a whole area, such as in green, and then if you cut it in half, let's say, and you look at this purple side and the blue side, the point is those are areas. And there's a lot of different quantities, which for whatever reason, you might want to compute on these areas. We might want to compute how much mass there is on these areas. We might want to compute how much work it takes to paint these areas, whatever, right? But likewise, you might want to compute boundary circulation for these areas, keyword areas, right? So it seems creepy and counterintuitive if I were to, looking at this picture right here, if I were to say, all right, I've got this total boundary circulation, that's 33. How much of that boundary circulation does this boundary circulation represent? They don't seem to be connected at all. The orange and the blue don't even touch. What do you mean, how much of the blue is in the orange? That doesn't make any sense at all, right? But if you think about it, again, as I claim we should, if you think about it in terms of areas, and let me just redraw that picture. How much of the accumulating quantity in question that we associate to this area, how much of that would we naturally associate to this area? And there's nothing weird about that at all, right? This orange region is literally a subset of this blue region. And so if I have this quantity and I can think of the whole as the sum of the parts, and I want to talk about the quantity in question, don't fall for the red herring. Don't be distracted by the fact that it's computed on the boundary. That's a distraction. That's not the point. I have an accumulating quantity that's defined on the blue region. I want to know how much is coming from the orange region. Just compute the quantity in question for the orange region, and there's your answer. Okay. So it takes a little bit of digesting. Later on today, I hope, fingers crossed, we'll see how fast I move. Otherwise, on Friday, I'm going to show you an analogous circumstance where this weird point of view here about stuff on the boundary actually happening in the interior. I'm going to show you an example where not only is it easier to see that it happens in the interior like I'm claiming, but you've already seen this example. And so anyway, I'm just going to leave that as foreshadowing for dramatic purposes. Yeah?
I'm a little confused because it feels like it's accumulating here.
Yeah.
Before it was like crossing out. So like what distinguishes this paper from the previous?
Yeah. No, it's the same. So for example, if I were to look at, let's see here. Let me make some color choices. If I were to look at this overall purple circulation around the whole boundary, right? Well, that's a bunch of pieces. That's this piece plus that piece plus that piece plus that piece plus that, et cetera, right? And then if I were to look at these individually, well, there's this and this and that, and there's this and this and that, et cetera, et cetera. And but it's the same deal that, like, if I were to look at like this edge right here, well, there's a green one and there's a blue one, and they have opposite orientations, and they cancel. Does that make sense?
Yeah.
Yeah. Okay. Yeah, it's a good question. Yeah. Yeah, it's very surprising. It's very counterintuitive. It's very uncomfortable. Take some time to, give yourself the time as needed. Listen to this lecture again if you have to. See the book's take on this, right? They're a little bit different, but take some getting used to. But again, good example coming later where I think will make this much more satisfying. Okay. All right. So we've dealt with accumulating quantities before, such as, for example, mass, right? And I can talk about, in this region here for, let's see, let me think more cleverly about my colors. Mass, right? And I can talk about in a certain area. Here's an area that I'm going to color in yellow. I can ask how much mass is there in that area. And typically we understand the relationship between the amount of mass in that region versus the area of that region by way of what we call a density, right? So the accumulating quantity per unit size, in this case area. Right? So this is an old idea. Mass per unit area is what we understand as a density. Okay, old news. So claim you can do the same thing for any accumulating quantity. Mass is nice because I'm familiar with it. I encounter mass every day, right? We see it. We have this idea of, density means, well, it's kind of heavier for a given size. Right? And low density means for, given how much weight it is, it's kind of big. Stuff like this. We just have great intuition for it. But structurally, this is no different than any other accumulating quantity where I could do the same kind of a thing. So for example, for a given amount of area, another perfectly good accumulating quantity for which I could talk about an associated density is circulation. So I can talk about the boundary circulation for this piece. Now, sure, again, it's computed on the boundary. Yeah. Distraction. Don't bite it. Don't bite that. Right? That's a distraction from the best point of view. Is boundary circulation is something you associate to the area, and you can still talk about how much of that boundary circulation there is per unit area, and likewise, this then is a density. And in the same way that up here we call this a mass density because the accumulating quantity in question is mass, likewise, hopefully no surprise, we're going to call this circulation density because the accumulating quantity in question is circulation. Yeah.
Do you mind explaining what exactly the boundary circulation represents? Because mass is like the amount of matter.
Yeah.
The boundary circulation behaves like physical stuff. Like
Yeah.
is that?
That's right. It's non-physical, right? The best explanation I can give you, I'm going to refer you back to some stuff we talked about a while ago, but boundary circulation, I conjured this image of a fluid, and the idea is if you were to drop a leaf in there, boundary circulation is a way of measuring, in some sense, how that's going to be rotating. Now, that's a physical way to think about it, but ultimately, deep down, the answer to your question is it's a mathematical expression. And so, how you want to visualize it, well, okay, there's, I suppose, different ways one could think about it. But ultimately, it's an algebraic construction. Yeah. So, again, unsatisfying, and I know, right? Because we love physical stuff that we can viscerally experience because it's very familiar. This won't have that. So that's the bad news. All right. Yeah.
Can you go back real quick to the one that had like all the interior sections?
Yeah.
In the middle one.
Oh, this one here. Yeah.
In the middle one that you've shaded, I know you said like you kind of refer to that like the whole being the sum of the parts, but in the whole, wouldn't that very middle one like have a boundary circulation of 0? So do we only?
No. The boundary circulation on this. Let me focused on this piece right here, I believe you were asking about.
So it's just the isolated piece.
The boundary circulation on this piece is 6.
Okay.
I just made up the numbers, but what that means is if I compute that line integral plus this line integral plus that line integral plus that line integral, that will add up to 6.
Okay, and then it'd be like what fraction of the total?
The total is the sum of all these individual ones. The total is 33. There's 6 is what it is for that one. And so the weird claim that I'm making is that the boundary circulation that we perceive around this outer, sort of the coastline, if you will, over here, right? That boundary circulation, 6 of that 33 is actually happening in here. And that's where I'm asking you to, use your imagination and, et cetera. Yeah. All right. Okay, so, so let me erase all of this junk, and in fact, I'm going to erase a lot of this as well, but I do want to leave boundary circulation per unit area, and there's a bunch of different things that we have to say about circulation density. For one thing, we have the term, we have the purple. We have a term. We have a kind of a motivation, right? There is also a formula for how to compute this. And I am going to sweep this under the rug. This is not something that I think is a good investment of time. I think it's much more valuable to have intuition about where it comes from, as opposed to the details of how to compute and prove the formula. But so details aside, computation aside, this is the result, as it turns out. For a vector field P comma Q, this little formula, dq dx minus dp dy, will tell you literally for any given little region how much boundary circulation per unit area there is in that area. Very surprising. Yeah.
Will we ever do this in 3 dimensions?
There's a version of this in 3 dimensions. It's pretty different, but yeah, it's not. It has a lot of the same earmarks as this, and there's actually arguably, depending on how you count, sort of 2 versions of this. Okay. Yeah, totally. But that's much later.
Okay.
Yeah, it's going to involve a different kind of integral that we haven't defined yet. Yeah. Okay, so name, intuition, formula. And now let's talk about notation and terminology. I like to call this Green's operator because you'll see why momentarily. This is the operator in what we're going to momentarily see as Green's theorem. So seems like a reasonable thing to me to call it. With that in mind, I like to abbreviate it as GRN. I find that satisfying myself. There are these 2 terminologies, notations here, rote and curl. Both of these are attempting to conjure what we were talking about, that somebody asked me about a minute ago, of, how do you visualize this? And I made this reference to, again, well, if you were to drop a leaf into the fluid, how is it going to be rotating around, right? Well, so thus the term rote for rotation. Okay? And curl, kind of conjures the same kind of, in some sense, kind of thing like this, right? So again, this is just a terminology choice. For whatever it's worth, I am a little bit uncomfortable with calling it curl, because y'all recall, we've already seen something called curl. It was 3-dimensional. It was a vector valued thing. It was not this formula. Didn't even really look all that much like this formula. It turns out, though, that they are actually somewhat closely connected. So, anyway, I don't really care for it because I feel like we have an abundance of reasonable things to call this, and why should we give it the same name as something that it's actually importantly different from? That strikes me as kind of unnecessary and counterproductive. That's just an opinion. It's very standard, perfectly reasonable, feel free. What I do have a legitimate beef with, though, is this one right here. This does not make any sense. We are talking about a 2-dimensional scenario. In 2 dimensions, there is no such thing as del cross. After all, there is no cross. To do a cross product, you need 3 coordinates. We don't have them. We have 2. That really doesn't make sense. What's the business with the dot K here? We're in 2 dimensions. We only have an I and a J. There is no K. Right? So now let me show you where they come up with this. And I don't think this is a good justification, but nevertheless, this is a point of view. If you were to take your vector field and pretend that it was P, Q, 0, which I emphasize, it's not. But if you were to just play make-believe for a second, let's attach a 0 on the end here as if that's something you're allowed to do. Now it's 3-dimensional. Now you can do del cross. You can then dot with the K vector 0, 0, 1. And if you were to do that, you would get exactly that formula. So that's why they would write it like this. But it's like, yeah, but it's not. Right? This is a 3-dimensional vector field. That's not what we're actually dealing with. And I don't see myself enough other advantages to this notation. I mean, what's my incentive to create confusion? What do I get out of it? Why is this better than my alternatives? I just don't see it. So please don't use this notation. I think this is anyway, I don't like it. How we doing? Everybody okay? All right. Okay, so let's put it all together. Quick reminders. We talked about the idea of boundary. Boundary is oriented. That's important. That's it's again arbitrary, but it's standard and it's necessary. It's necessary because we need specific orientations so that, in fact, these will cancel, so that we get the accumulation feature. This idea, this critical idea that this is an accumulating quantity only comes because we have a standard of what we mean by the orientation on the boundary. Right? That's what creates this opportunity for cancellation. So we have a boundary notion, we have orientations, we have the idea of accumulation, we have this idea of an associated density. And believe it or not, we actually now have a theorem. We just have to put the pieces together. And here we go. So let's start by thinking about this expression right here. That's circulation. It looks like an expression. It is an expression. I want to reevaluate it, reinterpret it as being a quantity. Don't think of this as a formula involving quantities. Think of this as a quantity itself. This is sigma. Okay, so we have this quantity. It's an accumulating quantity. The whole is the sum of the parts. So like every other accumulating quantity we've ever talked about, sigma is an integral of d sigma. Chop it up, add it up. Didn't really happen there. And then I've got this idea that stuff is equal to stuff per unit size times size, where stuff per unit size is my associated density. And again, Green's operator, what I like to call Green's operator, as we saw up here, Green's operator is just another notation for what I think you should interpret as circulation density. So with all that said, notice, nice punchline is that any circulation can be computed as a double integral over the interior of Green's operator. Very weird theorem, very counterintuitive. This, after all, is a one-dimensional integral to line integral. Right? This is double integral. They're totally different kinds of integrals. How could they relate to each other? Very surprising. Yep. Yeah, exactly. So the idea is that we have a domain D, and the curve over here that we're doing the circulation is the boundary of that same domain. Yeah, totally. Very surprising result. Let's see an example. So notice, first of all, we're being asked to compute a circulation. There it is. Line integral, we got a vector field, we got a curve given. There you are. I claim this is a circulation. Notice in the statement of the question, it didn't actually say circulation, right? All it said was line integral on this curve. You then have to look at the curve and recognize, hey, that curve is a closed curve. So this isn't just any old line integral. This is, in fact, a line integral on a closed curve, otherwise known as a circulation. Everybody good? All right. So how are we going to compute this? Now, just to, I guess, be fair, we could brute force this, right? This curve, clockwise oriented unit circle, I can parameterize that with like sines and cosines and a cleverly placed negative, right? We could straight up parameterize that oriented curve. We could plug in that parameterization into here. By the way, it's going to get weird because when you parameterize the circle, again, sines and cosines, that means I'm going to have e to the power of like cosine, which is nasty. And then I'm going to have, tangent of sine of t. That's weird. Right, so this is going to be a very difficult plug and chug. I don't even know how doable that is. Everybody with me? Yeah.
If this is a closed circulation, why don't you use the notation with like the circle and the unit?
Oh yeah, it's optional. It's kind of a sort of a reminder to the listener or to the reader that, by the way, I emphasize this is a closed curve. So some people like to do that. Again, you can, but it means the same thing if you don't. So it's optional. Yeah.
So whenever we read that there's a closed curve, this theorem will work?
Basically. You do have to be a little bit careful. There's a sticky wicket that I'm about to mention here. Yeah. But other than the one little stickiness, yes. Closed curves, Green's theorem applies. Yeah. Yes? I'm sorry. I should have explicitly said so. I was hoping context. Well, I forgot, but then after I forgot, I was hoping context would bring it up. The partial symbol here is a standard notation just for the word boundary. It just means boundary. Yeah. All right. So we have a circulation. Let's use Green's theorem. Wait a minute. Green's theorem that says that this is equal to that only applies if the line integral in question is on a boundary. And boundary, don't forget, the word boundary is a loaded word at this point, right? Henceforth in this class, boundary means an oriented thing. Oriented according to a certain convention. And so we have to ask, is this closed curve, is this a boundary? Is the clockwise oriented unit circle, is that a boundary? Tragically, it's not. Right? The clockwise oriented unit circle, it's going the wrong way. Not a boundary. Cannot apply Green's theorem. Everybody see the bummer there? Okay, so there's a nice little hack workaround. You might even be able to see this coming. We're only off by an orientation. So when I say that I'm going clockwise around the unit circle, that means that I'm just doing the exact opposite orientation as if I were going counterclockwise. And counterclockwise is a boundary. It's specifically the boundary of this yellow region here. Right, so the green curve is a boundary. I can apply Green's theorem to this green curve. Everybody good? So how do I deal with that? Well, I just have to recognize that the curve that I'm interested in and the curve on which I can apply Green's theorem, these are just opposite orientations of each other, and opposite orientations gives me a negative. Everybody good? Yeah.
So it always needs to go in the counterclockwise direction?
if you want to say boundary, and if you want to use Green's theorem, you need your left-hand side to be a boundary. Boundary means oriented according to the certain convention, which typically means counterclockwise. That's right. Yes.
Are all boundaries closed lines?
Yes, that's right. All boundaries are closed curves or collections of closed curves. So, like if you have holes in the middle, there might be several closed curves. But yes, closed curves. Yeah, that's right. All right. So with that minus sign accounted for, very conveniently, then I'm looking here now at a line integral around the boundary of my two-dimensional region. Boundary means I can apply Green's theorem. Green's theorem tells me this. And don't forget to carry that minus sign through, of course. And now double integral of Green's operator, and it's just a question of how would you compute double integral of Green's operator. We've turned one question that was looking like it was going to be really hard. We have now successfully turned that into a different question. Now a double integral instead of a line integral. I'm not immediately clear that this is an improvement. Right? And by the way, again, not every time you apply one of these theorems will it just fall into ease and convenience. It's kind of like with substitutions back in Calc 1. Y'all remember doing substitutions? And sometimes, if you make a good choice of a substitution, it'll turn a hard problem into an easy problem. But if you make a bad choice, it can turn a hard problem into an even harder problem. Right? So again, this is a tool, not a wand. Right? So use cleverly. So in this case, how are we going to compute Green's operator? Well, we're going to take our vector field here. We're going to apply Green's operator. Green's operator ends up being just, 2. Again, just apply the usual formula. We're going to take the x partial of the second component. That gives me 3. Then I'm going to subtract the y partial of the first component. That's a 1. So 3 minus 1. And then, of course, at this point, this integral is super easy. Got lucky. How we doing? Yeah.
I'm sorry, in the last step, how did you get to minus 2 pi? Like, what did you put around?
Yeah. Well, so I know what my domain here is this disk, double integral of a constant over a known area. Right, so it's going to be the integrand times the area. You could factor out this 2, for example. Once you factor out the 2, you have an integral of dA, which is literally you're just adding up the areas of all the pieces of D, which then gives you literally the area of D. Yeah. Is that cool?
Yeah.
Okay. All right. Okay, so there's our first example down. Please do be really, really careful about this boundary business. Again, can't emphasize this enough. Green's theorem is not a catch-all for any vector line integrals whatsoever. Any vector line integral you can just rewrite as this double integral. Absolutely not. This only works if your domain for your line integral is a boundary. Very important. Yeah. Okay. Oh gosh. Oh, there it is. Okay. All right. Next example. Weird curve. That edge, followed by that edge, followed by that edge, followed by that edge. We want to compute a line integral over that sequence of 4 line segments that we're going to call a curve C. Okay, so here's the thing about it. You look at that curve C, you kind of momentarily let's not worry about orientations, whatever, right? And it's clearly that's the sort of the border of this gray region that I've got filled in there. It's tempting then to call C a boundary, and it's not. The orientations don't go the way that they're supposed to quite. So what you'll notice, though, is that this part of our curve C is a boundary. It's a boundary of D1. Right? And now let's look at, let's see here, I'll use blue, I guess. This, let's see here, let me change my mind here. No, oh gosh, yeah, I wanted that to be out here, sorry. This, the other part of C, that other part of C, so green plus blue together makes C, right? But notice this is not a boundary. This is going the wrong way. It's going clockwise. Not a boundary. However, it is the exact opposite orientation of this curve, and that curve is a boundary. That is straight up the boundary of this gray region D2, and the light blue being the same curve opposite orientation is just the negative of that. How we doing? Everybody on board? So C by itself is not a boundary, but if you will, kind of the left part of C is a boundary. The right part of C is just the opposite orientation on a boundary. Thus that minus sign. Yes?
So they have to have this, they have to be the same shape for this to work, right?
Oh no, this just happens to be. I took a curve and I kind of broke it into pieces. Just happened to work out this way. For the details at the bottom of the calculation, the fact that they're the same shape.
And then it adds.
Yeah, later on, yeah, that's going to come up. But right now, my breaking down this the way it is doesn't matter if this shape is the same.
So if D2 is just like, let's just say like a circle and it was moving clockwise, you could still say that the boundary D2 was opposite that.
Yeah.
Okay.
Yeah. I can still any curve you can just put a minus in the superscript, and then you have the exact same curve going the other way. So yeah, totally. Yep.
Remember the previous example when you change C to C minus and back to add a negative sign before the like that?
Yeah.
So why are you not doing that in this case?
Why what now?
Why are you not doing that?
Oh, I will. I just haven't done it yet. Yeah. No, I'm just right now. All I'm saying is that. So what I have in blue here, right, is the sort of the right half of C. That's this in blue is part of my C curve, and I'm just observing that what I have in light blue is the opposite orientation of this dark blue, and the dark blue is actually a boundary. So that I'm just making statements about orientations and curves and which curves connect up to make C. How that relates to integrals, we will see momentarily.
But the light blue is not a boundary.
The light blue is not a boundary. That's right. Yeah, it just isn't. It's going the wrong way for you to use the word boundary. Yeah. Okay, so cool. Our curve is green plus light blue. Light blue is the opposite orientation on dark blue. And there's that minus sign you were looking for. Yeah. Right. So the opposite orientations between light blue and dark blue means I have to put this minus sign in evaluating the line integral. If I want to say boundary of D2, I have to put this minus sign to give me what I'm actually interested in, which is the light blue curve. Okay. And it's now all over but the shouting. After all, Green's theorem applies there because that's a boundary. Green's theorem applies here because, again, also a boundary. You got to compute Green's operator. That's some details. It turns out Green's operator is 9. Now I'm going to leave that calculation for y'all. Here's our vector field. Compute Green's operator. Make sure you get 9. Right? But that's just a matter of various, the x partial of the second coordinate minus the y partial of the first coordinate, and you get 9. And then you get a couple of easy integrals. Each one of these integrals here is just 9 times an associated area, And here's where the areas have to equal. Because these areas are equal, that means that these integrals are equal, and so the difference is 0. Everybody good? All right. Okay, here's another clever application of Green's theorem. Let's start with Green's theorem. Here it is. There's Green's theorem. Now, you'll notice that I'm applying Green's theorem here to a special vector field. It's not uniquely special, but it is a special vector field, 0, x. I'll show you why in just a second, why I want to apply it to 0, x. But what we have here in green is Green's theorem applied to 0, x. All right, so why did I want 0, x? And it's because of what Green's operator is. If you just straight up compute Green's operator for that vector field, you will get 1. Which is nice because now notice my integral here, I'm looking at the integral of 1 on a region, and of course that tells me area of the region. So altogether, if you again, clever choice having been made of this special vector field, what I have is a formula for computing area. This vector line integral will compute the area of the region that curve is the boundary of. It's kind of wild, right? Again, you think area is a two-dimensional thing. Vector line integrals are kind of, if you will, sort of one-dimensional things. It seems like a weird sort of mismatch, but it works because of Green's theorem. All right, now a notational point. Y'all remember this business about coordinate line integrals, and so you can rewrite any vector line integral in a sort of coordinate line integral form. And in this case, it's this. Most of the time, as I said before, I'm not really a fan of coordinate integral notation, but I think you got to give it its due. In this case, I think it's actually a little bit more compact and convenient writing it like that. Doesn't happen very often, but when it does, it's kind of handy. So when you see this theorem in the book or in other locations, it's usually written like this. It's usually written as boundary circulation of x dy equals area, just for sort of notational sort of compactness. Okay. All right. Now, how does this help us? Here's a separate fact. If you want to compute integral x dy, not on a boundary, if you want to compute integral x dy on a line segment, specifically a straight line segment, there's a really handy formula for how to compute this integral. It works out wonderfully convenient. It's always the average of the x-coordinates of the endpoints times the change in the y-coordinates between the endpoints. X bar delta y. Super handy. No calculus required. Snap. Right? Very convenient. Now, I'm going to leave this as an exercise for y'all to check, so please do confirm that. All you got to do is parameterize this line segment that starts at that point and ends at that point. That's a Chapter 1 parameterization problem. And then how do you compute this line integral? Well, that's a Section 6.1 pull back through a parameterization, plug and chug. And everybody should do that once in their lives. What you're going to find after you do some sort of algebra, sort of moving things around, that you can write it like this, which of course is like this. So nice little, nice practice problem. So how do we take advantage of this? Well, the theorem, the big theorem we just mentioned, was that boundary line integral of x dy gives you area. Well, if your boundary is made up of a bunch of line segments, then you can just compute that integral x dy separately on each of the line segments. So for example, let me just come down here like this. On each individual line segment, like that for example, on that line segment, you can compute integral x dy by this awesome formula. And then repeat, right? You have to add up over all of the lines. You got to go all the way around the boundary. So this has 9 separate pieces here. I would have to go across all 9 little line segments making up that boundary. For each one, I use, again, this formula to compute the line integral. Add them all up. That gives me the total boundary line integral, namely the area. And look how easy it is to actually do this. So on this first piece, x bar, I have to look at the x coordinates of the boundary points, take their average, and that gives me 6.5. That's the x bar. Right. Now let's look at delta y. How much does y increase? Y goes from 1 to 6. By the way, the direction does matter. Oh gosh. Notice this is not just a line segment, this is an oriented line segment. I'm going from here to there. So y goes from 1 to 6. That's an increase, not a decrease, right? So end minus start, and that gives me positive 5. And then, using this yellow formula up here, x bar times delta y gives me 65 halves, apparently, for that first line segment. Then repeat for all the line segments, and you just computed the area of that nightmare. That make sense to everybody? Now, you might think to yourself, seems like a lot of trouble. Fool you on that. I'm going to do it the old-fashioned way. Let me just walk you through what the old-fashioned way might be. The old-fashioned way, you would take this and maybe kind of slice it into separate little triangles. Something like that. Let's see, and that is 7 separate triangles, most of which are not right triangles. Most of the edges of which are diagonals, which means they're square roots. So we have weird side lengths, we have weird angles. You're going to be doing a ton of projections, right? And then multiplying the distances that you compute from projections times the square roots, which are the side lengths. The arithmetic's going to be horrifying. Right? This is not a good way to do it. So all of a sudden, this calculation right here, now I guess it does have a bunch of arithmetic too, but this is 4-function arithmetic. Better yet, no, I guess it's 4-function. There's some fractions we have to divide, right? But really easy arithmetic. Snap. No square roots. Simple. Okay, moving along. Let's talk about flux through a curve. Flux through a curve is a lot like flux through a surface. We end up with a formula that I hope looks very familiar. A pretty good way to motivate this, and I think this is another nice exercise. I think everyone should, if you're in the market for an exercise, right, think through for yourself, how would you motivate this formula for flux? And reminder, when we were doing 3-dimensional flux through a 2-dimensional surface, we talked about quantity of fluid per unit time moving through the surface. Here, we're going to imagine quantity of fluid per unit time moving through this edge, this little line. And if your fluid is going like this, then you're going to be looking at a parallelogram like so, and you're going to compute not the volume, but the area of fluid that passes in a given amount of time. And again, the geometry of the picture, and think about the area of a parallelogram, blah, blah, blah. Go through, feel free to shamelessly rip off the calculation we did back in chapter 3. It's areas instead of volumes, still highly analogous, and what you'll find is that this formula is what computes the quantity of fluid per unit time when you have a fluid flow. So nice fact. And we're going to entertain now the question. Oh, actually, are we? Let me look at the time here. We have 8 seconds. Okay, we will pick this up on Friday. Friday, we will talk about what to do with this. See y'all later. Yeah.
On this slide.
Here, just ask me after I get the thing. Yeah. Real quick, let me do